Okay, so first of all, Griffin, thank you so much for a really kind introduction, and I'm very pleased I can give this talk. And even though it would have been really fascinating to give this talk in person, I think I'm also enjoy very much actually to see actually the audience here. So thank you for turning the camera, and also I'm really delighted that so many people of you are actually joining here online. And so it's a huge, as I said, distinction and really true pleasure for me to give this presentation. And what I'd like to do in the 15 minutes that I was allocated for this lecture, I would like to give you an overview over the research we're doing in my field, and I'd like to apologize ahead of time to some of you because I have mostly chosen to talk about kind of both research fields we are engaged in, which is quantum optomechanics and photonic skip-scale frequency combs. And I'd like to touch base actually on both fields and give you an overview of what you can do when you confine light to small volumes for extended amounts of time. And so before starting, I also like to mention that a lot of the work that I'm going to present today is the work of very gifted PhD students, very gifted postdocs, and collaborators. And we enjoyed collaborations with a number of groups like Sunil Bava in Purdue, John Bowers, Christian Coos, Tobias Hare, Paul Seidler, mentioned a few. And also I'm very indebted to former co-workers. Um, um, Now, before I start, I really would like to actually give credit because often this is the last slide in the presentation, and so I want to make sure that this last slide actually is not kind of skipped due to time constraints. And as I said, the research we've been doing for now about 16 years, 4 years at MPQ in Garching, the Max Planck, and now for about 12 years here at EPFL, really is a teamwork of many people and collaborators that I show here in recent times, Neil Bava and Hao Tan. And also, I'd like to really thank a lot of my former coworkers. And I won't let all be able to tell them by name, but we have a long distinguished list here of PhD and postdoc, and I'd like to single out one person I'm going to talk about today. In the second part on frequency combs, actually, Jung-Kyu Liu, who now just recently joined USDC, has done some very important work on my group and actually highlight that group. There's also Hiram Go, actually, who is now at Shanghai, who also contributed extensively to this work. Okay, with this acknowledgments that I want to put here first, I like to continue and tell you really about the work that really drives kind of my research interests and interests in my group. And so, and in general, my laboratory, what I'm is very interested in developing systems with very low dissipation. And the dissipation in classical systems such as oscillators, pendulas, or also superconducting junctions is typically expressed in terms of the quality factor Q, which is nothing else than the product of the frequency of the oscillator times tau, its energy decay time. And this quality factor turns out to be really central in many of the applications. It determines the phase noise. It determines the coherence of reference cavities. It determines the force noise in atomic force microscopy, or for macroscopic quantum optomechanics, it determines the decoherence rate or the field enhancement for nonlinear optics. So generally, achieving a high quality factor is really a endeavor that, on the one hand, has a long history in precision measurements, but also, as we'll describe in the last 15 years, is high quality factor has really given rise to new physical phenomena that we're trying to exploit. And so high Q, as I said, really spans this large range of applications from force microscopy, AFM, tuning forks as done in quartz watches, superconducting junctions where the Q determines your coherence of the systems, to all the way to gravity wave detectors or FBAR filters that are used for filtering in your cell phones. Now, the type of device I want to talk about today are optical microresonators, and those will be guiding kind of principle in my group, and I'll explain what you can do with these microresonators. And I want to give first a bit credit actually to the really pioneers in this field, and the pioneer really being here some very early work at Bell Labs that showed that you can make optical whispering gallery resonators, so devices that can find light in small amounts of volumes for extended amounts of time. And the challenge in these optical resonators is to achieve a high quality factor, because light is easily scattered, it's easily lost, it's very susceptible to surface imperfections. And the big breakthrough was made in 1989 by Vladimir Beginsky, Michael Gordetsky, and Lutsenko, when they showed that just melting a piece of glass would give you quality factors of hundreds of millions, so which corresponds to 100-meter path length in just a very small little dielectric sphere. So that set the stage for a kind of, if you want, a revolution in coherence or quality factor in optical microresonators. Now, the type of work I'm going to talk about today really has its origin back work I did with Carvajal at Caltech. And I'm showing you here one device of a high-Q resonator, which today has proliferated. There are many more devices, materials, and platforms that are also fully chip integrated. But still, the physics that I'm going to describe today really can be studied in this prototypical kind of system. So what is this system? This system is just a piece of glass that's melted in a torus shape, and this gives very low surface roughness, and this gives quality factors more than 100 million. So that means, again, that path length is about 100 meters, wrapped in a diameter that's a fraction of a human hair. Now, what can you do with these optical microresonators? So these high Qs themselves actually give rise to new physics. And one of these physical principles that was discovered about 15 years ago is that these microresonators, similar to a wine glass, have mechanical modes. Okay, and so one of these modes is shown in the upper left. It's a breathing mode of 50 megahertz, and it turns out that this breathing mode is coupled to radiation pressure, okay, in the system. So, this observation therefore implied that any optical resonators can be engineered to host both mechanical and optical modes, but importantly, these two can be coupled. And the coupling mechanism is actually the forces of light, the same forces of light you use to cool atoms, manipulate atoms in the quantum regime. So there's an underlying Hamiltonian you can describe, where A dagger A is the number of photons, B plus B dagger is the mechanical oscillator coordinate, and this coupling factor G, okay, is the 0-point fluctuation of the oscillator times the G factor here, which is the frequency pulse parameter. So this parameter tells you how much your cavity shifts as a function of displacement, and I'll come back to that parameter in a second. So, this optomechanical coupling is now kind of really widely established, and it has given a toolbox by which you can manipulate mechanical systems in the quantum regime that I would like to touch base on. Now, at the same time, these very high quality factors also give rise to new principles of frequency comp generation. Okay, and I'll talk about that in my second part of my presentation. And if you build up light intensities to sufficiently high values, you can obtain a parametric oscillator that uses the Kerr nonlinearity. So here, the A's are different modes of the resonator that are actually, and this process annihilates two pump photons and creates a new photon at a different frequency, signal annihilator. And this process can give rise to a new way to generate coherent optical frequency combs. So let's get started with an overview of what can really be done with microresonators. So microresonators over the last 20 years have really advanced significantly. Today they can be chip integrated. They're foundry level. We heard about it. They're even commercially available also now by a startup in my lab. We started about 5 years ago. And they have quality factors of as high as tens of million in a fully integrated photonic integrated circuit. So on the one hand, you can study very fundamental physics with these systems, quantum optomechanics that I'll touch today. But on the other hand, you can also study kind of optical frequency comp generation, which is now at the verge of transitioning to actual applications. I'd like to complete, for completeness mention, I will not have time to mention this today, but there's also very active fields of combining optical resonators with superconducting microwave resonators and via the piezoelectric or electro-optic effect. It's a new field of cavity electro-optics or cavity piezoelectro-optics. We were also working on this, but we'll not be able to touch this today. And this field is mostly motivated by the idea of interconnecting different parts of the electromagnetic spectrum. Microwave signals for wireless communication, for superconducting qubits, and optics for long-haul communications. And here also, these high-Q optical microresonators provide a system, a platform, when you combine it with the Pockels effect or piezoelectricity to make converters that take you from the optical to the microwave or vice versa. I'll not talk about that, but that's actually a very active area in my research group. At the same time, I also want to mention that there's a very new field opening up, another application actually of microresonators and integrated photonics in general in electron microscopy. So electron microscopy has really seen revolutionary advances over the last 10 years. Today with cryo-EM, you can solve protein structures at the single base pair level. What we have introduced together with Klaus Ropers at the MPI in Göttingen is a way to use integrated photonics to manipulate the wave function of electrons. And we believe actually this could unlock a new toolbox, actually, a quantum optical toolbox also, because we're going to generate correlations of electrons and photons, of manipulating electron wave functions for advancing the frontier of microscopy. And so we have a recent paper that I'll not talk about, but there's another area that is presently opening in my group and that we are very actively pursuing with his group in Göttingen. So what I'd like to talk about today really is give you a flavor of the research that's done in quantum optomechanics, and also give you some of the basics of this and the history of this field. And so I apologize for those who may already be very, very familiar with this. So the interaction of light and mechanical systems has a very long history in physics. In fact, already as early as the 1960s, the Russian physicist Brzezinski considered the effect of light that is confined in an optical cavity, so two pairs of mirrors. And what he was interested in was to understand how one can use such an arrangement to make very sensitive position measurements. And the moment you change, for instance, the position of the end mirror, due, for instance, a force that acts on the mirror, it changes the cavity path length, the resonant frequency, and you can use this, therefore, to make a sensor of force. And the motivation for this arrangement here are modern gravitation wave detectors, which Vladimir Brzezinski was one of the intellectual kind of leaders on. And gravity wave detectors today, they use end masses that are harmonically suspended on mirrors. And therefore, they are susceptible to the effects of radiation pressure. And so if you have photons, each upon reflection, you have a 2 h-bar k momentum transfer. If you multiply it with the flux, then what you find out that you get a radiation pressure force that's proportional to the number of photons in the cavity, where g is the frequency pole parameter. Now, so therefore, this entire system can be modeled as a very simple kind of system where you have an harmonic oscillator, beta b, that's mechanical in nature. You have the optical field. They're coupled by a Hamiltonian that is nonlinear. Okay, that couples the photon number to the mechanical oscillator position. Without going into too much details, but you can work out, and we've done this actually early on in 2007, you can work out the quantum theory. And what you can find out actually, and this has been already predicted by Brzezinski as early as 1969, you can achieve a ponderomotive effect of electromagnetic radiation. What does it mean? You can actually cool or amplify the mechanical motion. And in the case of Brzezinski, he was mostly worried about the amplification process, because amplification can make the entire interferometer unstable. And in fact, this is also what has been observed experimentally. So in the year 2015, the LIGO interferometer at very high powers started to undergo an instability due to the amplification of the end mirror motion. So it's effectively a phonon laser with respect to the mechanical degree of freedom. Now it turns out that the same effect that's been observed in 2015 LIGO was actually demonstrated already much earlier. Actually worked at it with Kerry Vahala at Caltech in 2005, but we observed that this effect can occur in optical microresonators very naturally at kind of very low powers. It can not only be used actually to amplify mechanical motion, but also to cool. And so this provides, therefore, an ability to cool mechanical systems all the way to the quantum ground state and manipulate them in a quantum regime. And so over the last, so what is the toolbox that's really behind this? The toolbox that is used in optomechanics there are similarities to the physics in trapped ions. So if you have an optical cavity, the cavity will have a resonance frequency, so shown in green here. And now there's two kind of arrangements. You can have a laser field that is detuned exactly by the mechanical frequency from this cavity, either below the resonance frequency or above. And if you are below the resonance frequency, then photons that are entering the cavity can only do so by annihilating a mechanical quanta. And this process is quantum mechanically described actually by a beam splitter Hamiltonian, which actually annihilates a quanta in a mechanical oscillator and actually generates one in the optical cavity with higher frequency. So you can think about this as an anti-Stokes scattering. You increase the frequency of the laser light. This takes energy and removes it from the mechanical oscillator. That is effectively the equivalent of atomic laser cooling, but now for macroscopic mechanical oscillators. And this technique can be incredibly kind of efficient. So in our lab right now, we can cool mechanical systems down to the ground state where they reside more than 97% of the time. So it's a very efficient means actually to cool systems all the way to their very close to their ground state. On the other hand, you can also amplify mechanical motion by placing yourself on the upper side band where photons get scattered into the cavity, and then you have a so-called two-mode squeeze or amplification Hamiltonian. And this Hamiltonian generates photon and phonon pairs. So it actually can also be used to generate entanglement. And so this toolbox of upper and lower sideband driving, which we established and colleagues now about more than 10 years ago, is really the laid the groundwork to cool mechanical systems to ground state, achieve quantum current coupling, polymer squeezing, entanglement, and many other experiments. And so over the last years, there's been a whole proliferation of optomechanical systems ranging from suspended macroscale mirrors of LIGO all the way down to nano-optomechanical systems such as photonic crystals. And all these systems share kind of the same physics, even though their masses span like more than like 10 orders of magnitude, and also the frequency spans many orders of magnitude. The physics is all the same of this radiation pressure Hamiltonian. And so over the last year, and I will not go through this, but there's really been spectacular progress in the field. So starting about 10 years ago, vacuum gap capacitors, photonic crystals, membranes, or also these Brisbane gallery toroids can achieve a range of quantum phenomena, ranging from ground state cooling, quantum coherent coupling, entanglement, both of the optics and mechanics, coherent state transfer, and many other examples. And so it's a whole revolution that had happened in our ability to manipulate mechanical systems in the quantum regime, and thereby also implicitly test quantum mechanics on a macroscopic scale. There's also been a lot of theoretical work happening, starting from topological phase of light and sound, and new ideas actually how one can overcome the 3 dB limit of squeezing using dissipative and reservoir engineering approaches. And so these are reviewed in our review that we wrote with Marcus Assemeyer and Florian Markert some time ago, and really led now this framework of quantum optomechanics. What I want to do is take a bit deeper dive actually in optomechanics to give you also some ideas of what we are interested in contemporarily. And even though quantum optomechanics has been mostly about manipulating mechanical system in the quantum regime, it really is about precision measurements of mechanical motion. And to illustrate you the progress that the field has made over the last years, let me just show you this graph here. So this is a graph that shows you it's called 0-point motion. Okay, that's the yellow line, and that is the vacuum fluctuation of the mechanical oscillator. So these are the intrinsic, half quantum of energy that every mechanical oscillator has. And what you can see here is that in the early 2000s, the most advanced sensors that could measure such mechanical motion of nanoscale objects, such as small beams, were single electron transistors, SATs, or cavities. And what has happened actually over the last 10 years is that there's been a dramatic improvement in our ability to measure mechanical motion. And this has been an advance that is now more than 5 orders of magnitude of improvement over 10 years. And this is very rare in physics. You have rarely 5 orders of magnitude improvement in a single quantity over just 10 years. And this has been largely driven by optomechanical systems. And what I'd like to tell you today is an experiment that's already outdated. So we have, I think the record right now was done by MIT, my former PhD student, Vivesh Sudhir, who demonstrated, I think, more than 70 dB in precision below the SQL. And that means that we are really realizing a Heisenberg microscope. Our imprecision in mechanical motion measurement is below the vacuum level. And that means actually that our back action of the measurement starts to dominate. So we realize here a Heisenberg microscope in these optomechanical systems. So to give an example, what are some of the systems we're studying? This is an example of a silica glass disc that has a diameter of about 100 micron. It's coupled to a silicon nitride string that can vibrate. And to give you an example of how sensitive and how efficient this coupling of optics and mechanics can be, let me give an example here. So if this mechanical oscillator that's placed in a near field starts to vibrate, okay, it will change the optical resonance frequency of the cavity. And so these devices we've developed here in our clean room, and so we've developed processes to place the mechanical oscillator here that's made from silicon nitride in the near field of the optical cavity. And so the trick in this experiment is to use near fields, and the near field here decays evanescently, okay, with a characteristic length scale that is deep sub-wavelength. And this implies actually if the mechanical oscillator slightly moves, it changes its dielectric energy significantly. And this can be expressed in terms of the so-called vacuum coupling rate. And this G0 has a very intuitive meaning. It's effectively the shift of the optical resonance frequency associated with half a quanta of mechanical energy. And if we look at that number, actually for this device here, it's 15 kilohertz. And for those who are maybe familiar with laser physics, 15 kilohertz actually is a very large optical frequency shift you can easily measure. And there's optomechanical system where this number can even be large as a megahertz. Now in our system, the relevant quantity is not just the G0, but the so-called cooperativity, the C0. So where we divide G0 squared over kappa gamma. Kappa is the cavity decay rate, gamma is the mechanical oscillator damping. And this number has a very important meaning in optomechanics, it tells us what is the number of photons required to measure, okay, at the standard quantum limit, so which is the point at which you can resolve the zero-point motion. And for our system, we only need actually less than one intracavity photon average to measure at the standard quantum limit. So these are exceptionally sensitive force sensors, which, when you increase the number of photons in the cavity, you can measure deeply below the SQL in terms of the imprecision. And this is what we have demonstrated and done. So here's an example where we measure the in-plane and out-of-plane mode of our mechanical oscillator. There's modes that come from the cavity that I will not discuss. We can also model this and find our thermomechanical noise budgets. And what we can do now is we can focus on one of the modes and do a very simple experiment called feedback cooling. What we do in feedback cooling is simply we take the measurement record, feed it back onto the mechanical oscillator, and by feedback, we can actually cool the mechanical system passively, okay, by feedback, very close to the ground state. And if you do that, okay, we can reach a regime where at some point we'll start to see noise squashing. That again, I won't have time to go into detail, but I want to mention that our imprecision is sufficiently low, it's high, that we can cool the system to a occupation that is very close to the quantum ground state. So in this example here, the beam was cooled to about 1 millikelvin effective temperature. And this corresponds to ground state occupation of just 16% or about 5 phonons. So this shows that the optomechanical sensors are very explicit force sensors, not just of force, but also of position, by which we can implement, for instance, real-time measurement feedback techniques. Now, this feedback technique I've described is truly quantum feedback. And why is it quantum feedback? Because the position record that we have of a mechanical oscillator not only contains thermal noise of the environment, okay, because the oscillator is coupled to our cryostat at 4 Kelvin, but also it contains measurement back action. And in our system, the quantum fluctuations of radiation pressure, actually, they deposit about 2,000 quanta of phonons into the mechanical oscillator. And why is that? It's because of the Heisenberg microscope, because we're measuring so precisely the mechanical motion that we're very strongly perturbing the system. But our feedback actually can compensate this. And this means that what we have is not just a classical feedback loop, which is the outer part here, a plant, a sensor, control, and actuator, but we also have the quantum back action of the measurement that we need to take into account. And so how can you see that there is this quantum back action? Another way to see it is by noting that the light you send in the mechanical oscillator to interrogate and measure its position actually is squeezed when it's actually exiting the mechanical oscillator. And this squeezing comes from the fact that radiation pressure quantum fluctuations drive the mechanical oscillator, change the path length, and couple the amplitude quantum fluctuation to phase quantum fluctuations and lead to a squeezing. And this squeezing occurs exactly in this regime where your measurement, okay, starts to enter this Heisenberg region where the imprecision is below the vacuum fluctuations. And this can be also observed in our experiments. If you take a look at the light that exits from our optomechanical system, and if we make a strong measurement with an imprecision far below the standard quantum limit, we see actually the light that is emitted from the optical signal is squeezed. And squeezing is incredibly robust signature. So how does it work? How do you measure squeezing? You take a balanced homodyne. So the same laser that's sent into the optomechanical system is also used as a local oscillator with a variable phase. We can then block the signal from entering the homodyne interferometer, and we get the blue trace. And now something very non-intuitive happens. If you open and send light from the optomechanical system into the homodyne interferometer, your noise actually in a certain region drops. So it's a very kind of striking signature and shows here that we have quantum motives or quantum squeezing of light that is generated by a mechanical system. Now in this system, the quantum the squeezing is very small. It's only about 10%, and it's largely limited simply by the mechanical quality factor that is low in these experiments, about 400,000. And I'll give an example of how we can improve that significantly. Now, what can you do with this squeezing? One little example is you can use it for quantum enhanced variational measurements. So imagine you send a force, okay, into the optomechanical system by modulating like a second laser that acts on a nanomechanical beam, and you place that harmonic force right in the region of squeezing. It turns out actually that you can be more sensitive to the force due to the presence of squeezing than you could be if the system was operating in a regime where you are just operating at the quantum at the shot noise level, not sub shot noise as in this example here. And so we showed this technique, which is called quantum variational force measurement. And we can show that the enhancement of the signal to noise comes from quantum correlations in the two quadratures of amplitude and phase. Now again, here the improvement was moderate. Okay, the absolute improvement was only 1%, and it mostly was limited by the quality factor, which in this case was about 400,000. Now, the quality factor of mechanical systems is something that has made spectacular advances in the last years. And what I want to show you is that historically, and I take this graph here from Imboden, the quality factor of mechanical systems has heuristically followed a scaling whereby you lose mechanical quality factor if you reduce the volume of the oscillator. So carbon nanotubes, some of the smallest mechanical systems, had typically low quality factors, whereas microscopic ball sapphire crystals would have quality factors of close to 1 billion. Now, what I'd like to show you is that over last years, um, um, starting with work from Jack Harris at Yale and then Albert Schließer in Copenhagen, there's really been a revolution in the quality factors, and we have introduced several new techniques called strain engineering and also crystalline mechanical oscillators that now allow us to obtain mechanical quality factors that are in excess of 10 to the 9, like basically 3 billion at room temperature and 15 billion at moderately low temperatures. And these are some of the highest quality factors ever measured in both temperature ranges. On top of that, these are not just bulk oscillators, these are nanoscale oscillators. And so how does this work? Again, we'll not have much time, but one technique I would like to briefly mention is strain engineering. So our trick here is to use a long silicon nitride string that has a length of about 5 millimeters, a thickness of about 10 nanometers. And to give you the aspect ratio of that system, the aspect ratio of these mechanical strings is similar to the Golden Gate Bridge going from Los Angeles to San Francisco. So these are incredibly high aspect ratio, 10 to the 5, 10 to the 6 structures. If you taper these, you actually enhance strain in the middle region. A technique that's known in semiconductor industry to enhance the speed of transistors. And if we overlap that region with a mechanical mode by corrugation, we can achieve quality factors at room temperature of close to 1 billion actually in these structures. And if you go to more exotic, or not exotic, but more play also tricks with the actual mechanical oscillator and its boundary conditions and make those periodic, you can get quality factors as high as 3 billion, which we have forthcoming work on. So this is some of the highest mechanical quality factors measured to date, at room temperature for any kind of mechanical oscillator. Now, what can you do with these mechanical oscillators? You can perform quantum optomechanics at room temperature. So we can take a mechanical oscillator, couple to an optical cavity, and we should now be in a position to ground state cool and manipulate the system in a quantum regime, even in ambient temperatures, just what you can do with atoms and ions already today, now also with macroscopic mechanical oscillators. You can also play advances on materials. So this is an example of a work that just came out in Nature Physics last week. It shows a strained mechanical oscillator made from strained silicon. And here, using the same techniques of soft clamping, strain engineering, along with crystalline materials that don't have two-level systems, we can achieve now 13 billion quality factors. So these are ring downs that are as long, basically, as hours in these systems. So it shows that our ability to engineer nanomechanical systems has advanced to the point where we can we have extremely coherent systems which we can deeply manipulate in a quantum regime if you couple them to optical cavities. Now, quantum optomechanics also has possible future applications ranging from quantum noise thermometry, microwave to optical links where you interconvert between different electromagnetic signals, quantum enhanced force sensing. You can make detectors of radio waves using optics and light, or non-reciprocal devices. And the systems that we use in this technique of optomechanics is really ubiquitous. And I'd like to take a couple minutes to also show you that the same techniques of amplification, cooling can also be achieved in a microwave range. And so in my group, we have an ongoing effort since many years that uses so-called vacuum gap capacitors. So what is shown here in the SEM is our two plates, parallel plates, tens of micron in diameter that are just separated by 15 nanometer. And this plate here is a drum. It has a mechanical oscillator. And at the same time, it's a capacitor. And if you link this to an inductor, you have an LC circuit, and the exact same optomechanical physics that I've described of the mechanically compliant optical cavity can also be made for a mechanically compliant LC resonator. Now, these resonators are superconducting, so this aluminum, they're cooled down to typically tens of millikelvin. And we use the circuit QED toolbox to read out and amplify the microwave signals. And with these systems, we can also, for instance, to give an example, what we can do is we can generate very complex optomechanical systems that not only have one optical mode and one mechanical mode, but in fact, as shown here, could have two optical modes, two microwave modes coupled to two mechanical oscillators. And for instance, here we use the first order mode and second order higher mode of a drum. And what we can show that by sideband cooling the systems with multiple tones, we can generate a synthetic flux and synthetic gauge and generate non-reciprocity in those systems. And so in this example, what we have achieved, for instance, is a non-reciprocal frequency converter where microwave photons are sent in an LC circuit composed of two mechanical modes and two optical modes, and we can achieve non-reciprocal transfer of microwave photons. So again, I'll be only very brief here, but I want to highlight the fact that the optomechanics also applies to superconducting circuits, which we're very actively exploring actually in my lab. And to give an example of one very recent result, which we're very excited about, we have recently shown that you can make 1D and also 2D lattices, including topological lattices such as the SSH model, and use optomechanics to probe, for instance, the edge states and topologically trivial and non-trivial states in lattices of 1D and 2D electromechanical circuits. So these electromechanical circuits at low temperature in the superconducting devices are an ideal platform to explore these multimode optomechanics that employ multiple LC resonators and multiple mechanical oscillators. And there's recent work in the archive forthcoming that shows that we can use optomechanics also here as a new toolbox. Now, I'd like to, in the last 20 minutes, really switch gears and leave the field of quantum optomechanics and tell you about another facet of this physics of light confinement on chip in terms of optical frequency combs. And so what I've described is that optical resonators have inherent innate optomechanical coupling, but also they allow to excessive phenomena that's been known in only optics since decades, which is that of parametric frequency conversion. And this leads me to the second kind of part of my talk on chip-scale frequency combs. And in fact, more generally, I want to give you some ideas of what you can do with hybrid nonlinear integrated photonics. And so optical frequency combs, to briefly introduce them to this audience here, optical frequency combs were invented by Ted Henge and Jen Hall, who shared in 2005 Nobel Prize for them. And the idea that they introduced has been truly revolutionary. So they introduced the idea of using rulers for light, for the light field. And to make such a ruler for a light field, what they discovered is that if you have a mode-locked laser that emits short optical pulses, then in frequency domain, this constitutes a coherent series of equidistant laser lines, whereby the first laser line, the so-called carrier envelope frequency, provides an ambiguity in the Combs offset. And using techniques that Ted Henge and Jen Hall introduced, you can actually stabilize the so-called carrier envelope frequency. And if you do that, you make a fully stable optical router for light fields. And these optical frequency combs can be operated in two regimes. In one regime where they allow you to take an RF frequency and synthesize an optical frequency. So the frequencies here on the left are RF, on the right here optical. Or you can also do optical frequency division, whereby you take a laser stabilized to an atom or an ion that serves as an atomic clock, and you use the comb as a gearbox. So combs have remarkable number of applications. They are really the building blocks for some of the most precise atomic clocks. They have been used in astronomy, in spectroscopy, and many other related disciplines. However, there is over the last decades there has been the realization that one can open many more applications of frequency combs if one makes use of the advances in integrated photonics. Frequency combs to date, despite being one of the remarkably successful technologies, are mostly confined to specialized laboratories and metrology institutes. And in about 20 years, there's still only comparatively few optical frequency combs that are operated in laboratories, about 300 worldwide. This could change dramatically when one uses integrated photonics to make the technology not just smaller and more compact and scalable, but also if one can access its high repetition rates. In fact, for many applications, a frequency comb spacing of 200 megahertz is too little. And I'll give examples where the high mode spacing of tens of gigahertz is really imperative, such as optical telecommunications, where the channel spacing is, for instance, a multiple of 12.5 gigahertz. So how do these microcombs kind of work? So the physics of microcombs really goes back to parametric oscillations, which is very well known nonlinear optical phenomena. So if you pump a medium at high intensities, um, a process and the material has no inversion symmetry, the elemental nonlinear interaction is third order and therefore leads to a process by which two pump photons are annihilated and a signal and an Euler photon are generated. So this process, as said, is mediated by a so-called kernel linearity, or in the Hamiltonian description, you would also have to take into account the volume of the cavity. So the smaller the cavities, the larger this parametric coupling becomes. And this technique itself actually is also well known in the community of superconducting junctions, where actually it can be used to make parametric amplifiers. So in 2004, in fact, we demonstrated that you can generate the signal in either sidebands in an optical resonator at exceptionally low power. And not just that, if the rate of photon scattering into signal in Euler exceeds the cavity decay rate, you achieve and you reach a so-called parametric oscillation threshold. And this parametric oscillation threshold, importantly, scales with the inverse quality factor squared. So high Q cavities allow to dramatically reduce the threshold. Now, this generates signal in either sidebands, which are equidistant because you need to conserve energy. But what's more interesting is that this process can actually cascade. And in this cascade, there's many more complex pathways in which the photons interact, not just this degenerate path, also non-degenerate ones. And we demonstrated about more than 15 years ago that in fact these microresonators produce truly equidistant optical frequency combs. And we did that by comparing with the fiber laser frequency comb and proving that the comb spacing was accurate within 1 part in 10 to the 15. So that made clear that there's a new way to generate frequency combs that breaks the dogma that only mode-locked lasers that emit pulses can generate combs. And here you generate the comb directly from a CW laser. Now, these Kerr combs have really proliferated. Kerr combs have been observed in almost any material platform in indicator photonics to date, be it silicon nitride, high-dex, fused silica, calcium fluoride, magnesium fluoride, diamond, but also most recently 3,5 compound semiconductors, and also materials that exhibit second-order linearity like lithium niobate. And these devices attain repetition rates all the way down from 1 gigahertz to terahertz, and can achieve bandwidth that can even be octospanning or even beyond. And so there's been a very rich field that has opened that largely draws also from the advances made in integrated nonlinear photonic platforms. Now, one very important new kind of element in these microresonators was discovered more recently by my former PhD student Tobias, who's now a professor at Hamburg, and he observed that one can not only generate frequency combs in these microresonators, but also dissipative Kerr solitons. And so what are solitons? Solitons are waveforms that are shape preserving. Dissipative solitons are solitons that exist in an environment which continuously loses energy. And so solitons and optical fibers are effectively conservative systems. The optical fiber has very, very low losses, and solitons form and can propagate, but effectively the losses do not play any role. In optical microresonators, the way the solitons are sustained here is by the parametric gain that is compensated by the continuous loss of photons, the bus waveguide. These solitons, so-called dissipative solitons, are known since the 90s. They exist in driven plasmas, fiber cavities, and also they have been analog in spatial solitons. And so we can think of actually this effect of soliton formation resonator as a form of self-organization of light. And to show you kind of the self-organization of light, let me give an example here of a simulation. And what is done is a laser is tuned inside the resonator. And what we're doing is we're simulating the intercavity waveform. And there's now a framework of the so-called Tugato-Lefevre equation, which can be used to describe the mean field, okay, of all the intercavity field that is being generated by a pump laser. And so when you start increasing the power inside the cavity, there's a certain point, which is called the bifurcation point, where the cavity field itself becomes unstable, okay, and where you have effectively a modulation instability. And the modulation instability leads to pattern formation. And the pattern formation here inside the resonator, okay, shows that we generate something called Turing rolls. So these are, if you want, frequency combs with a spacing that is multiple of the free speckle range. And these are coherent structures. We can then enter a region where the system becomes chaotic and where inside the resonator okay, we have in fact not just a frequency comb. In fact, we have many, many modes. Even within one cavity line width, there are multiple modes. It's a chaotic kind of state of many, many frequencies that then miraculously, when you tune into the bistability region, can generate kind of solitons. And there's characteristic steps in our transmission spectrum associated with the soliton formation. In this case here, you see 4 solitons, and we've developed techniques by which we can switch the number of solitons down to all the way to 1. And so generally, what's really happening here is we have a system. So a driven optical microresonator follows a nonlinear dissipative Schrodinger equation, where the left-hand side of the equation is very well known. This is an equation that contains dispersion and contains nonlinearity, and the solution are solitons. But the right-hand side actually is unconventional. It contains loss, laser detuning, and power. And the detuning of the laser and the power span a 2-dimensional space, and this space tells us about the phases in the system. Now, I should mention this phase diagram is vastly simplified. In reality, it's a lot much more complex. But there's region where you have chaos, there's region where you generate solitons, and region where the solitons can breathe. And a lot of work in my group has been devoted to understanding this phase diagram, and then also understanding ways how to modify it. So we mostly operate in the stable soliton regime, and one of the aspects that maybe is striking about solitons is that they're very stable. So any optical resonator has imperfections, and these imperfections can include mode crossings, excuse me, or they come from other mode families. And the soliton itself will always self-stabilize and find a solution that is completely shape-preserving. So here's an example of a NMOS 3D kind of dispersion landscape, which has a lot of avoided mode crossings. But what you can see is that a soliton actually generates so-called dispersive waves and stabilizes despite the presence of imperfections. So these dissipative solitons are in fact not just idealized solutions of this Lugatti-Lefebvre equation, but they can even exist actually in the presence of various imperfections. So in fact, nature has a tendency to look for coherent dissipative structures. And we see those all around us, be it cloud formation, pattern formation in a desert. So here, at play is a very fundamental principle of nature, that of pattern formation, of modulation stability, Turing patterns, and also entailing soliton formation. So these solitons have also been observed in almost all platforms to date. They are coherent optical frequency combs, can be very broadband, and also very short pulses of light. Now, one important aspect to really transition these solitons into actual applications is to have a platform that allows to generate solitons in a manner that they can be used in true system-level applications. Okay, system-level applications meaning applications outside of the lab. And my lab has followed the pioneering work that was done by Columbia and with a group of Michael Lipson that first showed that silicon nitride is a very promising material for nonlinear photonics. So even though silicon nitride is already well known in the CMOS process and used as an edge stop layer and capping layer for decades, its use in indicator photonics is only very recently. And this is due to the fact that you have to generate very, very thick wavelength scale waveguides to operate in the proper dispersion region to generate soliton frequency combs. And what we have developed at EPFL is a technique by which the silicon nitride waveguides can be generated with ultra low loss that I'll outline in a second. Now, silicon nitride can generate combs, and here you see already some of the advantages. So if you pump one of the silicon nitride resonators, you see here, this is a 100 gigahertz device, and it covers the full C and L band. The pump is taken out for clarity here. And these are, for instance, sufficient to perform coherent communication experiments, okay, for telecommunications. We've also given commercial access to the technology. About 5 years ago, we spun out a company, Ligentech, that is making photonic integrated circuits. They have a PDK. They can make complex circuits like splitters, routers, heaters, etc. And our chips are being used not just by industry, but also by academics and also startups. And they also, and this may be less surprising, they are nonlinear. They can be used to generate 4F mixing. And for instance, this article on quantum circuits with many photons on a programmable non-photonic chip by Xanadu, a quantum computing company. In fact, this chip actually was built by Ligentech. It's so here in Switzerland. So another example of the use of these negative photonic circuits beyond frequency combs. We can understand the combs very accurately and very well. So we can model them by the Lugatti-Lefebvre equation. We have understood what modifications we need to take into account in terms of dispersion, in terms of Raman effect. And I just want to leave you with one image that we have incredibly good control and understanding actually of the envelopes of the combs, and know how to simulate these. We can use them, as mentioned, for coherent communications. We use a solid frequency comb as a sender, a second one as a receiver. We demonstrated this a number of years ago with Christian Koos, so really a system level application. We can also use them for LiDAR, where we can use each comb line and induce on each comb line a chirp and perform massively parallel coherent FMCW LiDAR. So each of the comb line here basically is the frequency is changed. So in time domain, what you can think about is that the repetition rate is the same of the soliton, but we just change the underlying carrier. This is actually one of the surprising features of solitons, that even in the presence of a chirp pulse, actually the soliton can maintain its shape. And this we have used, and I will not go into detail, to implement a very interesting technique of LiDAR called FMCW LiDAR that gives you both velocity and distance information in the same pixel. Together with Sunil Bava at Purdue, we also demonstrated that we can achieve advanced control over solitons. Here, for instance, by including piezoelectric MEMS, that we can achieve for very fast frequency actuation, where the piezoelectric, via the strain optical effect, actually is able to change and actuate very quickly on the optical cavity. And this system therefore combines electrical, mechanical, and optical degree of freedom, and is also a platform by which we're looking at making quantum coherent microwave to optical converters that I will not cover in this presentation today. As mentioned, we can use different ways of achieving ranging. This is an example again of this FMCW approach that I've described, that we now also have generalized to chaotic LiDAR and dual comb LiDAR. So generally, there's been a lot of applications of the solid microchromes. These are just the one my lab has been involved in. So we demonstrated massively parallel telecommunication in 2017. Another fascinating application, which I'm very fond of, is astrophysical spectrometer calibration, where we use the comb to calibrate spectrographs, coherent LiDAR, piezoelectric control, and also neuromorphic computing, as well as integrated turnkey solid microchrome. So all these platforms use our kind of silicon nitride damascene platform. But all these applications would not be possible if it wasn't for one reason, and that is having circuits with ultra low loss. Another aspect I want to draw attention to is all these applications, are applications that you could not do with conventional laser frequency combs. So the mode spacing for telecom, astrophysical spectrometer calibration, LiDAR, or even neuromorphic computing needs to be in the range of 10 to 100 gigahertz, and that is not accessible with femtosecond laser combs. So our microcombs, they are not replacing femtosecond laser combs. In fact, they're opening a new dimension with high repetition rate and compact form factor. Now, but really imperative to move this technology forward is one kind of one aspect that is often overlooked, and those are losses. So the very fact that I can give this presentation today to Beijing here in this remarkably fast internet connection is really due to the pioneering work of Charles Kao. And Kao actually in the 60s and 70s was studying what gives losses in optical fibers. And what his research found out is that impurities due to iron and copper in optical fibers lead to massive losses. And he understood if you take out the impurities of iron, you can make very transparent fibers. This has led losses now down to become less than 0.5 dB per kilometer, and has really triggered the whole revolution in long-haul communication. Today in integrated photonics, to about 10 years ago, our losses were about 1 dB per centimeter. And what I would like to describe to you is work that we have done to close that gap, that exists between integrated photonics and optical fibers. And I want to show you examples now where we can actually reduce that loss from 1 dB per centimeter to 1 dB per meter. And the way we have done this actually is to introduce a new manufacturing process, the photonic damascene process, by which we don't etch silicon nitride, but we deposit silicon nitride in trenches. And so this process is inspired from the VLSI copper damascene process, where you use copper interconnects to create a circuitry on an electronic chip, but here we use it for making circuitry on an optical chip. And to show you how low the losses can be made, let me show you this sample here that Junqiu Liu has demonstrated. This is a photonic integrated circuit with a path length of 1 meter that's wrapped actually in a chip here that's just 5 by 5 millimeter. And the loss that this 1 meter spiral has is just 1 dB. So it shows you actually that we have remarkably low loss integrated photonics that's a factor of 100 better that can be done in silicon photonics today. How does it work? We use a few tricks. One of the tricks is that we make a preform from glass, slightly reflow it to remove all the roughness. So effectively, we have roughness-free waveguides that still have preserved the lithographic control and wafer scalability in the process. And with this, we can make very compact microchromes that are even can be coupled to 3-5 laser diodes, and it can be truly kind of chip integrated and operate to give a very compact form factor of salt and frequency combs. So to show you some of the most complex device we've made, there's an example from a collaboration we had with John Bowers at UC Santa Barbara, where our Damascene silicon nitride resonators were packaged. We used the technique of self-injection locking, which we discovered with Michael Gordetsky at RQC. And this shows a quarter kind of penny from the United States, and this entire device is capable of generating a 50 gigahertz pulse stream of solitons. So it really shows that the technology has come to a point where it's very compact, it's scalable, and can also be used in applications such as data center interconnects for providing the channels for coherent communications. To give one example, some of the most advanced integration we have done with the group of John Bowers, where our silicon nitride Damascene platform has been integrated with also 3.5s and silicon interposers, where we've made a device that whose dimensions here are just a few millimeters per 100 micron. So on one wafer, we have thousands of optical frequency combs, salt and frequency combs. And so it shows that we can also make really a scalable technology out of this. Now, last, optical combs have many applications that I've described, clocks, distance measurements, coherent communications. But I want to zoom out and leave you with one kind of last slide, and that is the ultra-low loss silicon nitride integrated photonic circuits. They're not just a very interesting platform, in fact, for comb generation. In fact, there's many more platforms that are opened by this new platform. You can make frequency agile lasers that have the coherence of a fiber laser on a chip. We can make low noise microwave generators. We can bond the silicon nitride to lithium niobate, make thereby very efficient electro-optic circuits, and also we can make broadband parametric amplifiers. And so the whole platform of silicon nitride is much more than what I've just described. We can amplify light on a chip with it using so-called traveling wave parametric amplifiers. Or what we can do is we can make cryogenic interconnects, that use silicon nitride integrated circuits with lithium niobate on top to read out, for instance, quantum signals, from superconducting junctions, which we operate in our lab. And here, the really key advantage is that compared to a coax cable that runs down a fridge and has about 1 milliwatt of heating from the outside world, optical finders only have 10 microwatt. And a platform of silicon nitride actually is a building block to make very efficient transducers to convert microwave signals to optical signals, which we're also investigating in my lab. So with this, I've used the 50 minutes according to my clock, and I'll stop here and thank you very for your attention. Yes. Yeah, so you can. So have not gone through this, but we have done experiments showing low noise microwave generation in the X and K bands, so 10, 20 gigahertz, directly from a solid pulse stream. And it's maybe non-intuitive, but it's easier to generate a solid at higher frequency because the efficiency of solid generation, of bright solid generation, increases with repetition rate. So 300 gigahertz solid pulse streams can be very readily generated actually in these microcomb platforms. Rather, the opposite is challenging, to go to low frequencies, and that has to do with the fact that you lose volume, and also typically and that means that the threshold actually starts to increase when increasing the cavity size. So 300 gigahertz microwave signals even have been generated. The challenge there lies really more on the detection side and the conversion side. I hope that answered the question. Yeah, so in general, of course, this the process is quantum mechanical, and there's been very beautiful work I didn't cover, where one can generate effectively photon pairs and basically highly entangled cluster states using these microcombs. In fact, that's what Xana very briefly that I mentioned for the photonic quantum computing. They're actually using they're using forward mixing to generate correlations of photons. So now um, I think it's a very interesting. I think generally all platforms for quantum computing are very fascinating. Personally, I think that the superconducting qubits right now have a very large lead. Um, on the other hand, it is true that photonic quantum computing has some aspects that make it extremely enticing when it comes to scaling up the system. If frequency combs could have a role there, I think generally, processes that generate photon pairs are really what's required. The nonlinearity is the single photons. So the ability to generate with high efficiency single Eiler photons is certainly very promising. The biggest challenge there that we have seen in work with Hugo Psinden and Rob Thu at Geneva, in a group from Nicolas Gizin, who's really a pioneer in QKD, is that we always have Raman scattering. So for every signal Eiler photon we generate, we still have sometimes photons that come from Raman, and that I think is a large limitation in the ability to use these subthreshold parametric oscillators for photon pair generation. So we would have to work and understand how we can mitigate Raman to make really high fidelity single photon sources. Yeah, yeah. So what I showed is, if I go back in the presentation, what I showed is, so I should mention, so I've shown a number of cavities structures. What I've shown is the optical cavities with this photonic Damascene process, and there, what we can do today is we can make optical resonators that have quality factors of basically 30 million in a fully integrated photonic circuit. So that's almost as large as these reflown structures that were first described 20 years ago, but now in a platform that's fully chip integrated that you can run through a CMOS foundry, and also, and that's much more important, you can add more complexity, waveguides, splitters, detectors, etc. So that is with respect to the optical property. So there right now, best we can do is about Q factors of 30 million in the silicon ITAR platform. In terms of the mechanics, the story is a bit different. So mechanics really, what we use there, I'll go back to one slide, is we use effectively a process that I only very briefly touched upon, and that is the process of kind of strain engineering and soft clamping. So the reason these mechanical quality factors of these strings are so high is that they are under very high tensile stress. So similar to a guitar string that you tension, okay, the very fact that you tension the system reduces the loss tangent. So even though the material itself is silicon nitride and its bulk acoustic propagation losses are very high, the moment you tension the material, the acoustic propagation loss in a string, in fact, is reduced. And this is a technique called a loss dilution. And it was first described in gravitational wave detectors. And by applying now uniform stress, apply soft clamping and strain engineering, we can achieve these quality factors of 800 millions. But again, these are mechanical ones that we have. And these open now up the perspective to perform room temperature quantum optomechanics. In fact, that's what we are working on. We would like to achieve ground state cooling, quantum Seidman symmetry, bottom of squeezing all in ambient temperatures. And the challenges there are, on one hand, the mechanical coherence, but also to understand how you integrate optical cavities and to read out the mechanical motion and observe these polymotive effects. So I'm not sure if I got exactly the question. So if we can use optomechanics to generate the frequency comb, is that the question? Oh, I see, I see. Yeah, so that's actually so okay, that's a very, very nice question there. So in fact, this is so I would like to answer such that all the rest of the audience understands a bit what's behind because I think I know what you, no, I know the paper you've read and I know what you're thinking and I want to show it. So what we've recently demonstrated with the group of Klaus Ropers at the Max Planck is that if we pass an electron beam in a TEM, actually through an optical resonator, what we can achieve is we can phase modulate the electron wave function. In that experiment, unfortunately, we could not demonstrate the nature, the underlying nature of the electron, which is that actually of a frequency comb. Why is that? Because every electron that has interacted with the optical resonator will be frequency shifted by multiples of h bar omega, or both plus and negative. So you can think about it as a phase modulation of the electron wave function. And indeed, what we generate actually here is a frequency comb of electrons. And the reason at the moment we can't see the frequency comb of electrons is that the spacing between the comb teeth is h bar omega, but the energy uncertainty in each electron is a sizable fraction of h bar omega. And we have actually ongoing work right now to really demonstrate the frequency comb nature, okay, of the underlying electron. And indeed, with this approach, we can generate frequency combs of electrons, electron beams that can be used for potentially in imaging tech modalities, even though this is still very fundamental research is of just understanding how we can harness this electron light interaction. Yeah, so I would go kind of one so step back and say that at the moment, I mean, the microcombs themselves, they can already be very compact. They can be chip integrated, and but the future applications are not entirely clear. So there's plausible scenarios where one can use the combs for. I think one plausible scenario is just test that measurement. We use optical frequency combs in our lab that have a spacing of 250 megahertz. If you could have a self-reference frequency combs based on photonic integrated circuits with 10 gigahertz spacing, this could even be more advantageous for us. So I can foresee maybe as one of the first applications these chip-scale combs for test and measurements. There are, however, examples of where these low loss silicon ionophotonic integrated circuits already today provide solutions to problems. I can give potentially already one example that I don't think I have on the slide here, but we have recently found a new company called DeepLight.ai, and DeepLight.ai is concerned with making lasers for FMCW ranging. And I think I've explained briefly the principle of FMCW ranging. And I'll briefly go back to that slide. And FMCW is a kind of new technique, or not necessarily new, but it's a promising technique for LiDAR, for basically detect for autonomous driving, but also for just driver assistance. And it's been very challenging to implement because for FMCW, and I'll come to the slide to explain the technique, what you need are lasers that have exceptionally narrow line width. So this is the technique of FMCW LiDAR. What you have is a laser that is scanned, okay, very precisely, and the real challenge of this technique is the linearity of the ramp. And what we have shown is that with Sunil Bava, with the integration of piezo MEMS on ultra-low silicon photonic circuits, we actually have we can build lasers that have the coherence of a fiber laser with tuning speeds that are unprecedented. They can be tuned with bandwidth of 10 megahertz, a factor of 100 more than a typical fiber laser you can buy commercially, or even 1,000. And these devices, I think, have tremendous potential actually for many applications, fiber sensing, or today, or FMCW LiDAR, or in general as highly coherent laser sources. So even though the microcombs may not yet have the big application that is today on the market, I think there are applications on the horizon where they which comes, but there is already today a very clear application of the technology that's described here that we're pursuing with a new startup from my lab, DeepLight, that is commercializing these exceptionally narrow and frequency agile lasers, which can both be operated in regime of single line or multiple lines of these combs. Yeah. Yeah, exactly. So in general, the power in the solid actually is very important. That's actually why we've worked on chip amplifiers, and I didn't have time to go into detail, but I just can mention it briefly here. So so we have demonstrated two new amplifiers in my lab. The first amplifier is a parametric amplifier, which is pumped optically and uses the kernel linearity. So we have achieved here almost 20 dB gain on chip by just pumping a long spiral that's dispersion engineered. And so it can get really gained by lithography. But what we've also done recently is we have implanted silicon nitride with erbium, and we have a paper on archive where we have demonstrated 140 milliwatt of output power from just a 5 by 5 millimeter chip. And so this shows that we can even integrate the solid microcombs directly with on-chip area amplifiers to generate sufficient power, for instance, for coherent communications or for LiDAR applications. So I think LiDAR will always need high power, so it's certainly one of the challenging applications in terms of power requirements. But I think with on-chip amplifiers, as we've demonstrated them now, there's a very clear path of amplifying each comb line to a few milliwatt of power that we have already demonstrated, in fact. Yeah, I think what I can comment is that there's a number of very interesting nonlinear platforms, and I would say silicon nitride is not necessarily one of the. I mean, what makes silicon nitride stand out is compared to silicon is this large band gap of 5 electron volts that allows you to avoid two-photon absorption in telecom band. It has a few other very interesting properties. The first is Brouillon scattering. In fact, the speed of sound in silicon nitride is actually much larger than in glass, which leads to loss of confinement of phonons. And Brouillon scattering, for instance, is strongly suppressed. It's very weak. So if you propagate 10 watt of optical power in a fiber, in fact, you would get strong backscattering. Here in these chips, you can propagate 10 watt of optical power in a silicon nitride waveguide, which we have done actually in the work from Victor Brush, without damaging it. So that's actually another important ingredient of the platform. The other part is that the Raman effect is comparatively weak. Now, what I think is interesting about silicon nitride is that the intrinsic loss, which we also have measured recently, in telecom band can be very low. It can be as low as 0.05 dB, 0.005 dB per meter. So we're still far away from the fundamental limit of the material. However, it has a disadvantage. Its kernel linearity, due to the 5 eV band gap, is low compared to, for instance, semiconductors like gallium phosphide. or also silicon carbide. Um, so these are very promising nonlinear materials with collaboration with IBM on GAP and also collaboration with a group from Shanghai actually on silicon carbide. I would say silicon nitride right now, why the platform I think is so useful is that it's incredibly um, um, reproducible and very easy to manufacture. So today, for instance, with Light Tech, if you put your design in 12 weeks, you can tape out and have solid microchromes on your optical bench. For some of the new materials like gallium phosphide, it took me those are not accessible yet. So you cannot buy gallium phosphide insulator. You can't buy silicon carbide insulator in sufficient quality. And even if you could, then you have to look very carefully. What is the Raman effect doing? What is the Brougham effect doing? What is the roughness of the waveguides? And this Damascene process, which we developed, is really only applicable to silicon nitride. Why? Because you need LPCVD growth, which is a high temperature growth. So this technique here could not be applied to 3.5. It could not be applied to silicon carbide. And the advantage is here is that we can completely eliminate any roughness in the waveguides, and that's central to get these losses of 1 dB per 1.4 dB per meter that we can achieve. So in that sense, I think silicon nitride actually has a couple of really compelling features, and over the last 10 years, the progress of silicon nitride has been almost exponential, where some of the other platforms, which all look very promising, have kind of mostly due to accessibility reasons, kind of not been as widely proliferated as I would have expected. Um, so in that sense, it's not just the material's properties, but also you have to ask the question: how is the material synthesized? How is it made? How can it be etched? There are many, many questions, and so in that sense, silicon nitride right now, yeah, has naturally emerged as a leading candidate for nonlinear optics because of all these virtues that I just mentioned: easy to deposit, high band gap, ultra low losses, low Bruin scattering, low Raman scattering. So that's in that sense, it's a pretty ideal material. And again, no surprise, it's been used in CMOS for 30, 40 years as an end-stop layer. It has very favorable properties. Yeah, I can go back to the one slide. So the story behind the combs actually is really the work we did with Pascal Delhaye, who is now group leader at the MPL, is we were initially actually not set out to look at frequency combs. We were interested in generating signal idler sidebands that are quantum correlated. And what we noticed is that in some of the samples, we would generate very flat band broadband combs, and so the challenge to demonstrate that this is a frequency comb can be seen by noting that the distance between the lines here in these microchromes was 7 nanometers. And so, due to a very fortuitous circumstance, which was that I had the opportunity to work with Theodor Hensch at the MPQ, so the inventor of laser frequency combs, we could use a fiber laser frequency comb, which I also plotted here in the graph of 100 megahertz, and use that one to measure the frequency interval between the pump and, say, the first sideband and the pump and the second sideband and the third sideband. And that ability to use fiber laser frequency combs to prove the mode spacing was imperative to convince the community that this is an optical frequency combs. In fact, there was quite some initial skepticism because there's no mode locking, there's nothing that keeps all the phases in synchrony. So it's not a priori clear that the comb here is perfectly equidistant. And so it was a combination of serendipity and also the right measurement techniques that back 15 years ago with Theodor Hensch, we could demonstrate that indeed there is a coherent optical frequency comb generated from microresonators. I mean, yeah, I mean, I think the part of the story maybe that is that I would is cite here is kind of I would like to cite a comment from Jen Hall that he made in one of his papers, which says that today we often read just papers that are relevant to our fields, and who would have thought that femtosecond lasers that can be used to drill, punch hole in materials and eyes, right? can actually be used to measure and create optical atomic clocks. And I think the point is that what Jen Hall tried to make is that sometimes advances they take place not in your very field of research, but in adjacent fields. And 15 years ago, frequency metrology was clearly a different field than indicator photonics. Today, these fields are merging. And as I described also in my talk, the serendipitous discovery that we made with the group from Göttingen and Klaus Ropers now also indicates that there could be a new field opening by taking indicator photonics actually and really applying it to electron microscopy. And so, which again is a very different field with different language and different challenges. And I think that's often how scientific advances proceed, right? At interface to new disciplines. Thank you much for attending. Thank you so much, Griffin. And again, thank you for the invitation. Okay, bye bye.